So, how was everyone's weekend? Good, good. Spoiler-free thoughts on the exam?
What?
Spoiler-free thoughts on the exam?
There was this one question where the wording is very interesting.
Okay. But, okay, I mean, we can't talk about it obviously until everyone's taken it, but
Yeah.
I guess generally, otherwise, how did it go?
Other than that question, it was fine.
Okay. Yeah, I took a peek at the exam. There were some interesting problems, I'd say, but nothing too crazy for the most part.
I would love to see Captain Jack there.
Okay. Well, yeah. Let's keep the. I saw the exam, yes, but let's keep the thing spoiler free for now, so that way, in case some people need to take it, you know.
Sorry, I didn't realize that.
Yeah. That's still. I don't know. I'm just trying to make sure we don't get to specific questions of what question is this?
Okay, that's not bad.
No, you're fine. I mean, I guess it's not really spoiling anything. So I guess what were you gonna say?
No, I was just saying I would love to see Captain Jack Sparrow on the exam.
Yeah, that was an interesting one. Yeah. Yeah. I guess that wasn't really a spoiler. I don't know why I thought that. My bad. Anyone else thoughts? Alright, cool. Well, not really much in the way of announcements. Just quiz 7 is going to be next week, so still got a bit of time to think about that. But other than that, that's it. No announcements. There's no homework due tonight, so let's get right down to business. So, lesson 19: concavity, inflection points, and the second derivative tests. So. The premise is that we have let I be some interval in the real line, negative to positive infinity. So if f of x has a shape that looks like either figure below on the interval I, so what I mean by that is something that looks like either like this or like this, then f of x is said to be concave up on the interval. Concave up on the interval. So here's what I mean by that. So in this case, if we take a look at some tangent lines on the curve, or some segments of said tangent lines, so let's go ahead and draw some of those. Okay, so here's our tangent lines. Okay. So what you'll notice is that these tangent lines are below the curve. So tangent lines below curve. Or another way you can think of concave up is instead of thinking of tangent lines below the curve, you could think of these as part of a smiley face. So parts of smiley face. Okay. And so similarly, that's the first definition. The second definition is similar. So in this case, we have part of what's sort of a frowny face. So in this case, if f of x has a shape that looks like either figure below, then f of x is going to be, as you might have guessed, concave down. Okay. So what you'll notice is that if we draw some more line segments corresponding to the tangent lines, as you might have guessed, the tangent lines are now going to be above the curve. So, something like that. Okay. So now the tangent lines above the curve And in this case, you could think of this as part of a frowny face. Yep. So you might think, okay, well that's good and all, but how do we figure out what intervals we have concave up and concave down? Well, in this case, we're going to need to use some calculus to figure that out. So here's a useful fact to help us figure that out. So A, if the second derivative is positive for all x in I, then f of x is concave up on I. Okay? And similarly, for part B, if the second derivative is going to be negative for all x and I, in this case we have, as you might have guessed, concave down. On I. So you might think, okay, well that's good and all, but why is that the case? Like, how do we make a connection between the definition up here and this fact down here? Well, let's go ahead and draw a picture. So for part A, if we take a look at the second derivative is positive, well, remember, you can think of this as the same thing as saying, all right, well, this is the same thing as saying, all right, the derivative of the first derivative, well, because that's the second derivative by definition, that's going to be positive, right? So as a result, that says, okay, if we think of f prime as its function by itself, then what this says is that because the derivative of the first derivative is positive, then the first derivative is going to be increasing. Okay? Because the derivative here is positive. So, okay. So pictorially, to see what that looks like, let's take a look at the following. Okay, so here's our whole smiley face. So I'll draw 5 points. Okay. So draw our line segments. Okay. So what you'll notice is that, all right, well, here we have, these two line segments are going to have that the first derivative is negative for these two line segments. For this line segment here, it's a horizontal tangent line, so that's going to be f prime is exactly 0. And then here you notice, well, wait a minute, this has positive slope, so f prime is not going to be positive here on these two lines. So as a result, you say, all right, well, that means that f prime is going from negative to 0 to positive. So that's one way to see that. That's one way to see that f prime is increasing in that case. So pictorially, that's one way to see that. And then in a similar fashion, well, if we take a look at B, then what we notice is that if f prime or f double prime is negative, well, similar reasoning says that that's the same thing as saying the derivative of f prime is negative. So that says in this case f prime is going to be what in that case? So in this case, we had that the derivative of f prime here was positive, so that implies that f prime would increase. So if the derivative of f prime is negative now, And that says that f prime is going to what?
Decrease.
Decrease, right. Okay. Okay, so now if we draw our whole frowny face, then 5 points. Okay. So here's our line segments. So in this case, what you notice is that here we have, well, these are positive slope, so we have f prime is positive, and these two line segments. Here we have another horizontal tangent line, so this is f prime is exactly 0. And then here we have two tangent lines with negative slope, so we have f prime is now negative here. Okay. Okay, so what that says is that if f prime is positive, that means that f double prime is positive, that means f prime is increasing from positive to negative on a concave up function. And if f double prime is negative, well, that means that it's going to be concave down because f prime is going to decrease from positive to negative. Okay. Okay. So any questions on that part before we move on? Okay. So now the next definition, sort of related to the idea of concavity, is this idea of an inflection point. So, does anyone else still need page 1? Okay. So inflection points are going to be points where concavity changes, either from up to down, or down to up. Okay. Okay. So one nice thing about the way to find inflection points is that it's going to be extremely similar to finding critical points, except here we don't use the first derivative, we use the second derivative. So same procedure. So to find inflection points, same procedure as finding critical points, except now use the second derivative instead of the first derivative. Okay? Okay, so conceptually there's not much else to that. So now what we're going to do is now we're going to talk about this notion of the second derivative test. So in this case, what we have here is that we have let x equals c satisfy f prime of c equals 0. So yes, in this case, and then let f double prime exist on an interval containing c. So what this says is that, all right, so if f prime equals 0, this gives us a sort of quicker way to find a critical point in this case, or classify a critical point in this case. So in this case, if we have that f prime of c is going to be positive, then x equals c is a relative minimum. Okay. So one way to see this is that we say, all right, well, we saw, all right, so f double prime of c is greater than 0. Well, as we just saw, that corresponds to a frowny, or not frowny face, a smiley face. So if we have f prime of c equals 0, so we have c here, and we have a horizontal tangent line, and f double prime is greater than 0, so frowny face, sorry, smiley face, I don't know why I keep saying that. Been tempted to say frowny face a lot, I don't know why. So anyways, if f double prime of c is positive, that means we get a smiley face, and so we get x equals c as a relative minimum in that case. And then if f double prime of c is negative, well, as you might have guessed, x equals c is a relative maximum. And the way to see that is, well, if f double prime is negative, we get a frowny face here. And then f prime of c is equal to 0, so we have a horizontal tangent line. And c. So we have a relative maximum here. Okay, so that's how we can see that. So pictorially, second derivative test is pretty easy to see. So, but for the third one, if otherwise, so in this case, if f double prime is equal to 0, second dt inconclusive. So at this point, you need to use the first derivative test. Need first derivative test here. Okay.
So only when it equals 0 is when you use the first derivative test?
Yes. Yeah, because the thing is that even though the second derivative test is generally quicker, the first derivative test is always conclusive, which is exactly the remark I was going to mention now. So first derivative test, always conclusive, as in it always says it's either going to be a relative min, a relative max, or neither of them. But second derivative test is quicker if applicable. Okay. So taking that into account, let's go ahead and apply this to basically the only real example I had today. So in this case, let f of x equal 3x to the fifth plus 10x to the fourth minus 2. So in this case, we have 4 parts we have to figure out here. So we have to find the interval or intervals where f of x is concave up or concave down. Find the inflection point or points of f of x. Find and classify the relative extrema using the second derivative test. And then find the intervals where f of x is concave up and decreasing, and then as well as concave up and increasing. So to start off, let's go ahead and look at part A. So one thing to note here is that, let's take a look at the domain just to make sure we're all on the same page on this. So the nice thing is that since this is just a nice little polynomial, degree 5, that should pretty quickly tell you that its domain is what? Go ahead.
Numbers.
Yeah, our real numbers. So this, you can think of this as sort of a step 0. So the domain is going to be from negative to positive infinity. So the nice thing with this is that this generally holds in the context of this homework for all the functions you're going to encounter as well as their respective derivatives. So usually the case with all functions and their derivatives on the homework. Okay? Okay, so that's sort of a step 0, just to make sure everything plays out nicely in here. So now step 1. So in this case, if we want to find the intervals of concavity and the inflection points, well, in this case, we have to do a similar process as with finding critical points. So first we got to find f double prime of x and check where f double prime of x equals 0 or does not exist. Okay? So the thing here is that, well, if f of x equals 3x to the 5th plus 10x to the 4th minus 2, then f prime of x should then equal what? Or we'll say f and f double prime. So for f prime of x, a quick application of power rule should yield what? Yep, 40x to the third, good. And because we'll need this later, we should probably factor this now. So if you take a look at both terms, what do they have in common? Let's give someone else a chance. So if you notice, regarding the x's, they both have x cubed in common, right? So we can factor out x cubed, but what about the constant coefficients? What do they have in common? Yeah, just 5, right? Okay, so as a result, that says, all right, if we factor out 5x cubed out of both terms, we should end up with, well, 3x for the first term, and then plus 8 for the second term. Okay? And we don't really need this quite yet, but it'll help in a little bit later on when we get to part C, so it's good to have it now just so we have it. Okay? And now f double prime of x is going to equal what?
Yep, 60x cubed plus 120x squared.
Yep. X squared. So if we factor that as much as we can, we get what?
X squared and x plus 2.
Yep. Okay. So that takes care of that part. So now the next 2 pages are just scratch work, so yeah.
Do you recommend always factoring out f prime of x before moving to f double prime of x? I mean, at least for me, it was just easier just to go straight from 14x to the 4th plus 40x cubed straight down to the double derivative and just factor that out.
Yeah, no, in that case, you will want to apply power rule going from here to here, but the only reason I'm factoring is because when we get to part C, we're going to need to eventually find the relative extrema. So before we do that, we got to find the critical points. So I'm just factoring it now, so then that way we have it when we get to that point.
Okay.
So, okay. Any other questions on that? Okay. Okay, so now, step 2. Step 2. So, as with critical points, we have to draw a number line, but in this case we have to do so for f double prime. Okay? So in this case, what we have to do here is say, all right, in order to be able to find our candidates for inflection points, as before, we have to take our function f double prime of x and check where it's equal to 0 or does not exist. Now the thing is that, as stated in step 0, the domain of f and consequently f double prime is the set of all real numbers. So in this case, all we really have to do now is just check where the second derivative is equal to 0. So, if you set this equal to 0, that should pretty quickly tell you that the 2 candidates for inflection points are x equals, well, 0 and negative 2. So, I'll go ahead and say that those are our 2 candidates. So now, let's go ahead and draw our corresponding number line. So f double prime. So now we say, all right, so here's -2, here's 0. And again, I'm going to put 0 here just to indicate that's where the second derivative is equal to 0. Okay? Now the nice thing is that as with the critical points, that means we have to focus on 3 specific subintervals of the real line. So in this case, we have to deal with, to find concavity intervals, pick x values in each interval to plug in to f double prime of x. Okay. So in this case, well, if we notice our real number line, that should pretty quickly tell you we have 3 intervals we've got to work with here, right? So we have -infinity to -2, -2 to 0, and then 0 to infinity. Okay? So, in this case, we say, all right, in each of these 3 intervals here, which x value do we want to pick from each of these 3 intervals to plug into f double prime? So let's start with -infinity to -2. What would you want to plug in?
-3.
Yep, equals -3. That's a good one. And then for -2 to 0? -1. And then 0 to infinity, a good one would be, pick your favorite number. 1. Okay. So now if we plug those into f double prime, well, again, as with critical points, we don't care about the specific number, we just care about the sign of said number. So we plug them in. And in this case, to make things a bit easier, we should probably plug them into our factored form we've already established up here. So if we do that, we say, all right, we have 60 times some negative number, quantity squared, and then -3 plus 2, so again we have another negative number. So in this case, that's going to be strictly negative, because we have a negative squared and then just times a negative. So because of that, we say, all right, because we have a negative number here, that means that all numbers here, when we plug them into the second derivative, are going to yield a negative second derivative. So because of that, we're going to label our number line as such. We're going to put 2 negative signs here, and then a little frowny face to indicate concave down. Okay? You look a bit confused.
No.
Okay, I wasn't sure. Sorry.
No, all right, no.
Okay. So that's the first interval. Now if we do a similar thing for the other 2 intervals, and plugging in -1 and +1 into f prime, what sign do we get for each of these?
Negative and positive.
Negative for this one?
No, positive.
Positive, right. Because remember, we have 60 times some negative number squared. But then we have -1 plus 2, so that's going to be positive. So that's going to be positive here. And then for f double prime of 1, we should end up with what?
Positive.
Positive, right. Because 60 times some positive number squared plus times positive is going to be greater than 0. Okay? So here, in this case, what we're going to do here is we're going to put a little 2 plus numbers and then a little smiley face to indicate concave up. And then similar thing for the third interval. Okay? So that should pretty quickly tell you that, well, the only concave down interval is going to be from negative infinity to negative 2. But for concave up, so in the context of the homework, do you remember the convention of what happens if we have two intervals of the same property back to back?
You just combine them, so the interval is just negative 2 to infinity.
Exactly. So like we had in lesson, what was it, 17? No, sorry, 18, my bad. So in the so as what we had in lesson 18, so concavity doesn't change at x equals 0. So include x equals 0 in concave up interval. Okay. Okay. So that gives you your concavity intervals. So that's essentially part A. So any questions on that part before we move to part B? Okay. So now part B is more or less a follow-up to part A. So with part B, we have to find the inflection points of, so we have to find inflection points, IPs, of f of x. So what we notice here is that of our two candidates of x equals 0 and x equals negative 2, well, we only notice that x equals negative 2 is the only place where it changes sign, right? So concavity only changes at x equals negative 2. So in this case, well, that should tell you that there's an inflection point in this case. So in this case, since we have the function given to us now, we actually do need the whole point. So in this case, we need negative 2 comma f of negative 2. Okay? And again, we have to plug this back into the original function. F of x. Okay. So if we use a calculator on this, so if we plug in negative 2 back into the original function, then what should we end up with as a numerical value for this?
I got 62.
Okay, I agree with that number. So that means your only inflection point is going to be at negative 2 comma 62. So that's part B. So nice quick little follow-up to part A. So moving on to part C, unless anyone has any questions on any of what we just did. Okay.
So when you're finding the inflection point, it doesn't matter. It's just where it's changing in concavity, right? It doesn't matter if it's up, down, or down, up, just wherever it's changing.
Yeah, because in this case, we only care about where it changes concavity. So we don't care about, specific, in the way it specifically does so. Because in the case of increasing and decreasing, we do care because that actually corresponds to a specific definition for relative extrema. But here we don't have any definitions for, changing up to down or down to up. So it's just if the concavity changes, inflection point. Okay. Okay. So part C, or any other questions? Okay. Part C. So in this case, we have to find and classify relative extrema. So classify relative extrema with second derivative test. Okay. So in this case, if you want to find the relative extrema, well, we have to use our first derivative So first, solve f prime of x equals 0, because in this case we don't have any points where the first derivative does not exist because it's the polynomial. So in this case, we only care about where the first derivative is equal to 0. So 5x cubed times 3x plus 8. So if we set that equal to 0, that should pretty quickly tell you that your two candidates for extrema are going to be what?
Zero and negative 8/3.
Yep, x equals 0 and negative 8 over 3. Okay. So that takes care of that. So now what we're going to do is say, all right, let's plug each of these x values into our second derivative. So now, plug into f double prime of x. Okay? But here's the thing. We already saw what happens at f double prime of 0, right? So in that case, since x equals 0 was a potential candidate for an inflection point, well, that meant that this was going to be equal to 0 already. So this means that we have to use a first derivative test to figure out what's going on with x equals 0. So here, second derivative test inconclusive. So need first derivative test. Okay. But now, with the other critical or other candidate for a extrema, if we plug in negative 8/3 into our second derivative, well, what do we notice? So of our three intervals that we established up here, which of these three intervals contains negative 8/3?
From negative infinity to negative 2.
Exactly. So negative 8/3 in negative infinity to negative 2. So by what we established up here, since it's concave down, that must mean that this here is also negative. Okay? So by the second derivative test, we have a relative max at negative 8/3, comma f of negative 8/3. Okay. And again, we have to plug this back into our original f of x. So this one's going to be a bit trickier. So if you plug this negative 8/3 into a calculator and plug this into the original f of x, what fraction should you end up with?
I got 8,030 over 81. I don't know if that's right.
8,030. I got something a little bit different. Let's see. I got negative 2,560 over 9. So, sure what you did, but in any case, that would be what your function value would be here. Okay. So now to figure what's going on with x equals 0, we're going to have to use our number line for f prime. So to figure out x equals 0, use number line for f prime of x. Okay. So here's the nice thing with what's going on here. So f prime. So we have negative 8/3. We've got 0. 8/3 and 0. So, oh yeah, sorry. So with negative 8/3, we already established that this is a relative maximum, right? So already this gives us what's going on in these two intervals right away. Because, remember, with the relative maximum, we have that the first derivative is going from positive to negative. So because of that, that says, all right, we already have that this is going to be from positive to negative because of that. Since this is a relative maximum. Okay? So all that remains is all we need to do now is figure out what's going on at x equals 0. So if we, or for any x greater than 0. So in this case, if we were to plug in, say, x equals 1 into our first derivative, then f prime of 1, if we plug this into our factored form up here, should yield what sign? You should be able to pretty quickly see positive or negative. Positive, right? So we have positive here, so we have positive, so we have increasing to decreasing to increasing. So that should pretty quickly tell you that we have what kind of extrema at x equals 0. Minimum, right? So relative minimum at 1 comma f of, oh sorry, not, we have at 0 comma f of 0. Okay? But the nice thing with letting x equals 0 in the function is that that should pretty quickly tell you that the corresponding y coordinate is just 1. If we look back at our original f of x. Negative 2, right? Because in this case, this is 0, and you're just left with negative 2. Okay? Alright, so that's part C. So, any questions on that part? Alright. Okay, so now let's take a look at the last part, which sort of puts everything together, so to speak. So now part D. So now we need intervals, or interval, where concave up and decreasing, and concave up and increasing. Okay. So in this case, what you notice is that we have the one property that involves the second derivative and another property that involves the first derivative. So what would be a good idea to do from this is to say, all right, let's go ahead and put the number lines corresponding to the first, second, and first derivatives back to back, or side by side. So put number lines for f and f double prime side by side. Okay? So here's what I mean by that. So in this case, what we have for f double prime, we have f prime. Okay? So what I'm going to do is say, all right, let's go ahead and say for f double prime, we had candidates for inflection points at -2 and 0. And then for f prime, we had 0 and -8/3. Okay? So what happens with this is that for every x value where we have either the first or second derivative equals 0, what we're going to do is we're going to draw a sort of a dotted line here on each of these. So, okay, so the reason we do this is to say, all right, if we redraw our number lines, breaking up each number line here into however many intervals we have that are formed from this. So in this case, we have, well, -infinity to -8/3, -8/3 to -2, -2 to 0, and then 0 to infinity, then what we notice is that if we break up our real line into those 4 intervals, let's go ahead and redraw our number lines based on what we've already established. So with f double prime, we already have, okay, so from negative infinity to negative 2, we have that the second derivative is negative. So we have negative signs to account for that, and and for negative 2 to 0, and for 0 to infinity, we have plus signs to indicate the second derivative is positive. Okay. And then do a similar thing for f prime. So in this case, from negative infinity to negative 8/3, we have a positive first derivative. And then from negative 8/3 to 0, we have a negative first derivative, so we have negative signs here. Then from 0 to infinity, we have a positive first derivative, so that gives us that. Okay? So here's what that says. So like we've already established, f double prime being negative is going to be concave down, and f double prime being positive is corresponding to concave up. Okay. And then as we've already established in a previous lesson, f prime being positive is increasing. So increasing here and here. And then for f prime negative, we have decreasing. Okay. So if that's the case, putting all this together says that, all right, for our interval or intervals where we have concave up and decreasing for f of x, so in this case, what interval or intervals do we have that the function f of x is concave up and decreasing? If we take a look at what we have.
0 and infinity.
Concave up and decreasing? Or
Negative 2 to 0.
right, because we have concave up and decreasing from negative 2 to 0. Negative 2 to 0. And then similarly, for concave up and increasing, that should pretty quickly tell you that's going to be 0 to infinity. Okay? And then that's it. That's part D. And that's the entirety of lesson 19, essentially. Okay? So any questions on any of that? Okay, well, that's all I have for today, so enjoy your 2 extra minutes of freedom, and I will see you guys on Friday. And, oh yeah, I should probably also mention that I have Zoom office hours again tonight, but I'll post that in an email. It's going to be from 6 to 7. But otherwise, that's all I had, so have a good day.